Welcome to the video on L'Hopital's rule and the Maclaurin series. So L'Hopital's rule is that if a limit as x approaches a of some function over another function is indeterminate, then your limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of the numerator over the derivative of the denominator. So your indeterminate forms would be something like 0 over 0, negative or positive infinity over negative or positive infinity, infinity minus infinity, 0 times infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. And if your result of using L'Hopital's rule is indeterminate, you can use the rule again and take the second derivative to see if it's still indeterminate. So for example, if you have the limit as x approaches 1 of the natural log of x over x minus 1, if you plug in 1, you would get the natural log of 1 over 1 minus 1. The natural log of 1 is 0, and 1 minus 1 is 0, which is one of our indeterminate forms. So we can go ahead and take the derivative of the numerator and denominator and have the limit as x approaches 1. The derivative of the natural log of x is 1 over x, and the derivative of x minus 1 is 1. So this would equal 1 over 1, which is 1. So your limit as x approaches 1 of the natural log of x over x minus 1 is 1. Next, we have the limit as theta approaches 0 of sine of theta over theta. So our sine of 0 over 0 is equal to 0 over 0. So that's indeterminate. So we would do the limit as x approaches 0 of the derivative of sine of theta, which would be cosine of theta, over the derivative of theta, which is 1. Our cosine of 0 over 1 is equal to 1 over 1, which equals 1. So that's how you would use L'Hopital's rule. Next, we have Maclaurin series, which is a power series that estimates the value of a non-polynomial function with a polynomial function. So if we had some function f of x, it's going to be equal to the sum from k equals 0 to infinity of the kth derivative of f at 0 divided by k factorial times x to the k. So you would have f of 0, then your first derivative of f evaluated at 0 times x, your second derivative of f evaluated at 0 over 2 factorial times x squared, your third derivative of f evaluated at 0 over 3 factorial times x cubed, and so on. So your Maclaurin series will exist as long as the derivative exists. And it can be used to replace complicated expressions with a polynomial approximation for easier derivatives and limits. So for example, it says write 3 sine of 2x plus 5 as a Maclaurin series. So the 3 would stay out front. The derivative of sine of 2x is cosine of 2x times 2, and then the derivative of 5 is 0. So this equals 6 cosine 2x. Our f double prime of x is going to equal, our 6 stays out front. Our derivative of cosine of 2x is going to be negative sine of 2x times 2. So this equals negative 12 sine of 2x. Our third derivative is going to be negative 12 times our derivative of sine of 2x, which is going to be cosine 2x times 2. So that's negative 24 cosine 2x. And then we'll do our fourth derivative, which is negative 24 times the derivative of cosine of 2x, which would be negative sine 2x times 2. So that equals a positive 48 sine 2x. So we can evaluate all of these at 0. So f of 0 equals 3 sine of 2 times 0, so 0 plus 5. Our sine of 0 is 0. So this is just going to be 5. For f prime of 0, we'll have 6 cosine of 2 times 0, so cosine of 0. Our cosine of 0 is 1, so this equals 6. For f double prime of 0, we'll have negative 12 sine of 2 times 0, so sine of 0. Sine of 0 is 0, so this will equal 0. For f triple prime of 0, we have negative 24 times the cosine of 2 times 0, so cosine of 0. Cosine of 0 is 1, so this is negative 24. And finally, for our fourth derivative, evaluated at 0, this is 48 times the sine of 2 times 0, so sine of 0. Sine of 0 is 0, so this is 0 as well. So our f of x will equal f of 0, which is 5, plus f prime of 0 times x, so we have 6 times x, plus f double prime of 0, which is 0 over 2 factorial times x squared, plus f triple prime of x, which is negative 24, over 3 factorial times x cubed, plus the fourth derivative evaluated at 0, which is 0 over 4 factorial times x to the fourth. And that would technically go on forever. So this is going to be 0, and this is going to be 0. 3 factorial is 3 times 2 times 1. So we'll divide 3 from our negative 24, so that's negative 8. And then we'll divide our 2 as well to get negative 4. So f of x equals 5 plus 6x minus 4x cubed. So if you were taking a limit or a derivative, you could use this instead of this function for an approximation. So here we have our first IB practice question. It says, using Maclaurin series, find the limit as x approaches 0 of f of x equals 3 sine of x minus 3x plus 1/2 x cubed plus 1/8 x to the 6th over x to the 5th. So if we did that limit of 3 sine of x minus 3x plus 1/2 x cubed plus 1/8 x to the 6th over x to the 5th, this would equal our 3 sine of 0 minus 3 times 0 plus 1/2 0 cubed plus 1/8 0 to the 6th over 0 to the 5th. Our sine of 0 is 0, so all of this is going to equal 0 over 0. So what we want to do is we want to find what our 3 sine of x is using Maclaurin series. So we're going to make a polynomial approximation. So we need our f of x, our derivative of that, which is 3 cosine of x. We'll do our second derivative, which is negative 3 sine of x. Our third derivative, which is negative 3 cosine of x. Our fourth derivative, which is 3 sine of x. And then our fifth derivative, which is 3 cosine of x. So if you notice, it starts repeating itself. These here are the same as these. So your derivatives will start repeating your functions from before. So we want to evaluate these functions at 0. So f of 0 is 3 sine of 0. Sine of 0 is 0, so this is 0. F prime of 0 is 3 cosine of 0. Cosine of 0 is 1, so this is 3. F double prime of 0 is negative 3 sine of 0. Sine of 0 is 0, so this is 0. The third derivative, evaluated at 0, is negative 3 cosine of 0. Cosine of 0 is 1, so this is negative 3. Our fourth derivative evaluated at 0 is 3 sine of 0, which is the same as this one, which is 0. And then our fifth derivative, evaluated at 0, is 3 cosine of 0, which will give us 3. So our Maclaurin series will be f of x equals f of 0, which is 0, plus the first derivative evaluated at 0, so 3 times x, plus the second derivative evaluated at 0 over 2 factorial times x squared, plus the third derivative evaluated at 0 over 3 factorial times x cubed, plus the fourth derivative evaluated at 0 over 4 factorial times x to the fourth, plus the fifth derivative evaluated at 0 over 5 factorial times x to the fifth, and so on. So all these zeros would turn these terms to 0. So f of x equals 3x. 3 factorial is 3 times 2 times 1. So our 3 in the denominator will cancel with our 3 in the numerator. So this becomes negative 1/2 x cubed. And then 5 factorial is 5 times 4 times 3 times 2 times 1. Our 3's will cancel. So we'll get plus 1 over 40 x to the fifth. So we can go ahead and plug that into our original function. So we'll have our limit as x approaches 0 of 3 sine of x, which we said is approximately 3x minus 1/2 x cubed plus 1 over 40 x to the fifth, minus 3x plus 1/2 x cubed plus 1/8 x to the sixth all over x to the fifth. So we have 3x minus 3x, which is 0, negative 1/2 x cubed plus 1/2 x cubed, which is 0. So we have the limit as x approaches 0 of 1 over 40 x to the fifth plus 1 over 8 x to the sixth all over x to the fifth. So if we divide everything in the numerator by x to the fifth, this will turn into 1, and this will just turn into x. So this becomes the limit as x approaches 0 of 1 over 40 plus 1 over 8x, which equals, that'll go to 0, so this will just equal 1 over 40. So that would be our answer to this question. Now we have our second IB practice question, which says, using L'Hopital's rule, solve the following limit. The limit as x approaches 5 of sine of x minus 5 over x squared minus 3x minus 10. So this will equal the sine of 5 minus 5 over 5 squared minus 3 times 5 minus 10. So this equals the sine of 0, which is 0, over 25 minus 15 minus 10, which is 0. So since it's an indeterminate form, we're going to take the derivative of the numerator and the denominator and then use that in our limit. So we'll have the limit as x approaches 5 of our derivative of sine of x minus 5 would be cosine of x minus 5 times the derivative of the inside, which would just be 1. Then our denominator would become 2x minus 3. So now we'll do our limit for that, which will equal the cosine of 5 minus 5 over 2 times 5 minus 3, which equals the cosine of 0 over 10 minus 3. The cosine of 0 is 1, and 10 minus 3 is 7. So our answer would be 1 over 7. So in summary, L'Hopital's rule is if the limit as x approaches a of f of x over g of x is indeterminate, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And these are your indeterminate forms. If your result using L'Hopital's rule is indeterminate, you can use L'Hopital's rule again. A Maclaurin series is a power series that estimates the value of a non-polynomial function with a polynomial function, and you would use this to do that. And it exists as long as the derivative exists. And your Maclaurin series can be used to replace a complicated expression with a polynomial approximation for easier derivatives. That's all for this video. Thank you for watching.